All right, so we just made this discovery that there's this brand new force out there that's keeping all of our nuclei together. And so we have our nuclear strong force, which is essentially fighting against the electrostatic force to keep our nuclei from just flying apart, right? So because of the repulsing force between all of the protons. So this balance between the electrostatic force and the attractive force is very important in keeping our nucleus stable, as you can see. The strong force has one particularity, that it's short range. So that means that as your nuclei get larger and larger, so with greater numbers of protons and neutrons, the electrostatic force is going to have more and more of an influence. So just imagine as the size, as you increase the number of nucleons and the size is getting larger, that means that the strong force is not going to be able to keep it all together, and the electrostatic force is going to have a greater effect. So to compensate for that, you can see that this graph is important because it shows you the number of neutrons on the vertical axis and the number of protons on the horizontal axis. And you can see that if everything was growing so that we would keep the same number of neutrons and protons, like we could for small enough nuclei, as it turns out, we would not be looking at nuclei that would be stable anymore. So all the dots on this figure show you the nuclei that are stable. And as you can see that those nuclei, the stable ones over here, tend to have number of neutrons that are larger than the number of protons. So essentially, as you're increasing the number of nucleons, making your nuclei larger, what happens is that you need to actually add more neutrons to compensate for the growing electrostatic force. All right. So um, if we were not to add those neutrons, then we would have too much electrostatic force. So we can add more protons because then that would increase the value of the electrostatic force because those are charged. So we add more neutrons to increase the value of the strong nuclear force. And you can see that then the N over Z increases as we see the number of nucleons increasing. And eventually we get to a point where we don't see any more stable nuclei if our number of nucleons is too large. So you can see that beyond 209 nucleons or Z greater than 83, we've basically reached our limit there. All right, so if we look at, so we're going to talk about radioactivity now, and we're going to see what happens when unstable nuclei are going to decay into a stable nucleus. Or decay to their ground state. So a number of phenomena can happen. So we have, if we have an unstable nucleus, we're going to see that we have three different types of decays that can happen. And in these decays, either the nucleus is going to decay into a stable nucleus with different value of N and Z, and that's going to, we'll see what that happens for alpha decays, or it's going to return to ground state. So for example, what we'll see for gamma rays. So these three processes will be, so different particles will be emitted. So alpha particles are helium nuclei. So essentially they consist of two neutrons and two protons. We have beta decays where we're going to see emission of electrons and positrons. So the positron is the antiparticle of the electron. It has the same characteristic, the same mass, but opposite charge. So it's the same charge as an electron, but positive. And gamma rays, which are high energy photons. Okay. So what is interesting about these is that they have very different penetrating abilities. So when we hear about radioactivity and we hear about radiation, um, um, we have to be careful when we look at penetrating abilities, because gamma rays versus alpha rays will not be quite as have the same type of danger associated with them. So, for example, alpha rays, you can shield yourself with a sheet of paper and you're okay. Beta rays, they will penetrate more. So, beta minus refers to the electron, beta plus to the positron. They're going to penetrate a few millimeters of aluminum. So that's, that has a higher penetrating power. But gamma rays is where you have to be very careful because they are highly penetrating and they will go through several centimeters of lead. All right, so looking at each of these decays, starting with the alpha particle, so alpha rays. Here we start with a sort of generic nucleus. So as you can see, are using our previous notations. And X represents the parent nucleus. And we're going to emit an alpha particle. So that's our helium nucleus that you can see over here. And so you can see that because the helium is here and it has 4 nucleons, that means that the daughter here is going to have A minus 4 nucleons. And since it has 2 protons, we have Z minus 2 protons. Y here refers to the daughter nucleus, and you can see here an example with the number of neutrons, protons, and seeing where they end up. So some of the go towards the alpha particle and some go towards the daughter. So the next one is the beta decay. And again, this is where we're going to look at an emission of a positron or an electron. So we're going to start with the basic and we'll see in the next slide. It's actually a slightly more complicated, but the idea is to convert a neutron to a proton. But because the neutron doesn't have a charge, we need the product to be neutral also. So in the when that happens, we have a proton that is positively charged and an electron. So the overall stays neutral. Okay. And what that looks like for a nucleus, so we have our nucleus over here, and you can see that one of our neutron is going to change into a proton in this case. So that's why we see Z plus 1, no change to A because the number of nucleons stays the same. It's just that one neutron turned into a proton, and then we have an emission of an electron. If we were to look at the other type where we emit a positron, it's very similar, except that now we lost a proton and gain the positron over here. So this type of decay is something that we call a two-body decay because we start with one thing and then we end up with 2 other things. We know the energy of the daughters and basically we have some expectation to what we would see for the energy of our positron or electron. But as we actually look at the emission of those better particles, we actually see that we have a spectrum versus something that is emitting at the same energies. And that tells us that there's something else going on. And as it turns out, there is a third particle that is being emitted. It was just very difficult to detect because this particle is neutral. It has very, very, very little mass. So it's actually very difficult to detect. And it's called a neutrino. So we have the neutrino over here. I wouldn't worry too much about the bar over here. That's usually something that we use to show that we have an antiparticle. But again, not to worry too much, but just know that there is a neutrino that is being also created during this reaction. The last one is the gamma ray, which again is an electromagnetic wave. And this is for a nucleus that goes from an excited state to back to the ground state. And so how does our nuclei become excited? It could be from an alpha or beta decay. And we could have, so this is an example of sequence that you can get. So we have here a nucleus that goes through a beta decay. And then we have a daughter that's in an excited state and then goes to the ground state and emits a gamma ray. The star here is indicating an excited state of a nucleus. And so here, so we're going to have, so the decay that are going to, so in sometimes you're going to have one decay and be done, but a lot of the times, if you have especially heavier nuclei, you're going to essentially see a series of reactions that are going to happen. And so you can have a heavy nucleus that's going to decay using alpha emission, and then it's going to be followed by beta, etc. And so, so if you see the example here for uranium, you can see that you start with a very large number of nucleons, 235. And by the time you get to the first stable isotope, you're down to 207 nucleons. So you can actually see that here on this diagram. So you start all the way here, all right, with your mass number, atomic number, and you go through an alpha decay, followed by a beta decay, and then alpha, and etc. So you can see a chain reaction kind of here before you get to your stable nucleus. And so what we're going to see in the next video is, so we can see that we have a chain reaction here, and we'll talk more about chain reactions soon. But also it'd be nice to get an idea of the timeline. So this is we see the decays that are happening, but depending on the nucleus, we'll see that these reactions are going to happen fairly quickly or take some time. And that's something that you can use to our advantage. So for something that's going to take some time to decay, like carbon, we can use carbon-14 to get an idea of how old something is based on how many carbon nuclei have decayed or not. So in the next video, we'll talk about half lives and get an idea of, we'll talk about activity and get a little bit more of an idea of how long these reactions or how long our nuclei are going to stay, even our not so stable nuclei are going to stay in their state before they start decaying. All right.